Okay, on to homework 2, part 4, or part D. The question we have is explain and derive the heat diffusion equation for cylindrical coordinates and simplify what I just said for the case of steady state with no heat generation, no heat flow only in radial direction, and with that yield an expression for equivalent thermal resistance analogous to that in electrical currents, similar to what we did in part B. So I just have I have our diagram here that I stole off of the internet and just wrote or drew it here. So we have our R here, and then our dr is this cross-sectional area. We have our d theta here, and then we have our r d theta here, and then we have our phi here and our d phi here. Okay, and then the two things I have here are just our volume and our heat accumulation, or I guess, yeah, net heat equation. So let's get started. We can start with phi. Okay, so we're just going to do the linear approximation, or interpolation, sorry, of these as we've done in the past already. So q phi plus d phi equal to q phi. You still see my iPad? Okay, cool. Q phi dq phi over d phi d phi. Okay, cool. And then we can just further simplify. So all we did in that step was just simplify. And then we can go on and apply Fourier's law. I'm just going to output FL. Do this, getting pretty good after doing it how many times? Right. Okay, yeah. This should be fine. So after we applied our Fourier's law to our linear interpolation, that's what we get, and then we just need to simplify our equations, which we will get. Okay. Awesome. So recording, good. Okay, so we can box this up. That will be our final answer for that direction. And we will use this later, so I'm just going to go ahead and copy this down now because I know we're going to need it later and I don't want to write it again. I'll just put it down here. Then let's do our radial direction next. So we can do R. I'm just going to circle these so it's easier to tell where I'm at. Okay, this one should be a little easier, hopefully, than the phi, because it's just a lot of confusing numericals or numbers and stuff. So our area here is going to be r squared sine theta d theta d phi. Okay. Now we can do our linear interpolation. So QR plus DR is equal to QR plus DQR over DQ or DR. DR. Looks good. Then we can just simplify to do the same as we did before. I'm just writing it fully out instead of doing it quickly like I did last time. So you can see here and here I simplified. It's just on this part, on this one I actually wrote it fully out. So this is what you would get, but then these two values inside cancel, which just give you the negative. So this would simplify to negative dqr over dr. Okay, so now we can do the Fourier's law again. Q net R so we got our negative k times our area, so I'm just writing our area again, and then temperature gradient, I guess not temperature, just a gradient. Then we can simplify this to be dr, dance reflection, k r squared dt dr, and then volume. Okay, cool. That was easier than the first one for sure. Move this up just so I have room. Copy this down. And then a box. Okay. Finally, we'll do theta. So to get q theta plus d theta. Right, okay, yeah. So we'll get, well actually let's do our area first. Area equal to, area equal to r sine theta dr d phi. Okay, that helps a little bit. So linear interpolation. Get q theta plus dq theta d theta d theta. I'm not going to write out the up here again. They'll cancel out similarly as they have in the last two. So we'll get negative dq theta theta d theta. Okay, now we apply Fourier's law again and get, okay, still recording, theta. Okay, cool, right? Okay. Just kind of looking up what I did above and subbing in values when I remember right. No squared this time. And then now all I'm doing is just simplifying what's on the left. Or I guess moving around stuff, not necessarily simplifying. Okay, cool. So we got our final answer for that. Box this. And now all we have to do is energy balance. So we're going to use this here. Our Q in and Q out will be what we just solved for. So we can do that quick. I'm going to move these down because we're definitely going to need more space on that. That might be enough. So we got CP, DT, DT, and then our area. And then it will be these three added together. Actually, I'm not even going to write them out. I'm literally just going to bring these up. I'm going to copy this down because I'm too lazy and don't want to write them out again. Copy them for a reason. So we'll get this, and then I'll just drag these over. I'll just add plus signs here. Oops. And then get rid of this part. So that will be our energy balance, and then all we need to do is divide by CP and also divide by our area. Very messy, but so yep, that's what we'll get, and then let's write out the final altogether. So on the left we'll have dt dt, temperature gradient, and we'll have alpha with our k over cp, but we gotta remember r squared here. And then all of our areas will cancel, so that will cancel, cancel. And then we'll be left with d squared t. I'm just writing from what's above right now, nothing special. And then we have to remember from above our this value, our QdV. And then that also what we divided over gets carried over too, so our v's cancel, so we'll be just left with our dv will cancel, so we'll just be left with q over cp. The r, I don't think the r would be there because it's not needed. So yeah, this would be our final answer for question 1. Okay, on to part 2, which is simplify d1 for the case of steady state with no heat generation and heat flow only in the radial direction to yield an expression for the equivalent thermal resistance. So I wrote out here steady state, no generation, only radial direction. So steady state, we'll get our temperature gradient 0, and then no generation, we'll have that equal 0, and then we'll have only radial direction. So we'll have our theta and phi being 0, and then here I just have our circuit or voltage equations that we'll be using in like 5 minutes or so. So everything's still recording. Let's get into it. So we will, looking from this equation above that we boxed a second ago, we'll only be left with 0 on the left because we have it right above 0, and we'll have k over r squared, and we'll have ddr r squared dtdr, because yeah, okay, I was just checking. And then since we're equal to 0, this can kind of just go away. It will equal 0, so we'll just pretend that doesn't exist. So just erase that. Okay, cool. So we need to integrate again. We need to integrate here. So we have integrate, and then once we integrate, we'll have r squared dt dr plus c1 equals 0. So when we solve for c1, we'll get c1 equals r squared dt dr. And then if we want, we'll have c1 over r2 equals dt dr. We'll use both of those on a later. So we need to integrate again. So when we integrate again, we'll get when we integrate again, hold on. Okay, there we go. We'll get, sorry, my case is kind of broken. Get dt equal, well, I mean, I'm just writing what we have over here again. Nothing crazy. dr, because we multiply by dr. And when we do that, we'll get dr c1 r plus c2. And then again, we gotta add Fourier's law. So FL, and we'll have Q is equal to K 4 pi R squared dt dr. KA, yep. Okay, cool. So that was easy. Then we're going to plug in, or we're going to add our C1, because dt dr up here is equal to C1 over R2. So we're going to have Q is equal to K 4 pi R squared times C1 over R squared. And then we'll have these cancel. which will give us, and we want to solve for C1, so let's just do that now. So we'll have C1 is equal to Q over K 4 pi. Okay, cool. Getting there slowly but surely. Then all we have to do now is we'll get dt dr is equal to Q over K 4 pi times 1 over r squared, because we plug that back in, and then just integrate again. Which will give our delta t, which is what we're looking for our voltage equations, and we'll just have Q, will stay the same, and then this will just become, geez, oh, minus not. Awesome, so now we got that. So okay, so all we need now is just kind of separate these terms. I don't need another page. Bring this up. So now we're just going to rewrite our delta t in its different way just to show everything better. So that doesn't need a bracket. So all I'm doing here is just pulling our Q out to show our similarity to our voltage equations. Okay, so we have up here our voltage equation. Where is it? Oh, right here. So here we have our voltage equation of delta T is equal to Q resistance. So we have delta T is equal to Q times this whole quantity, which is just going to be a resistance. So we have Req is equal to 1 times, yeah, let's just write it that way, it'll be easier. And you can put Rk back so it looks better. So that will be our final answer to the equation, to the question. And that's how we relate our D1 to electrical current and thermal resistance.